Okay, this is Algebra 2, and we are in Unit 5. We're starting Lesson 1, and I'm going to break Lesson 1 into two separate lessons because it's kind of a little bit longer lesson, and a lot of this should feel like review. A lot of this stuff was talked about in Algebra 1, and we have used concepts of this throughout other math classes, so it should feel kind of comfortable for you, and hopefully it does, because that'll help you feel more confident. So starting off in this unit, we're talking about polynomial functions, and breaking down polynomials to like a more smaller base concept would be monomials. And mono means like one, and that's what that prefix means. And so when we have a monomial, this is a number, a variable, or a product of numbers and variables. And we'll talk about some examples of those. Really, a monomial is like one grouping of terms. Okay, we usually don't have like plus or minus signs. When we start putting monomials together, separate terms together, that's when we get polynomials. So a monomial could be just a number, it says. So it could be something like the number 4. It could be a variable and a number, or just a variable. It could be like x. It could be a number and a variable, so it could be like 5x. Or we can even add exponents to that. So we could have like 7x squared. Okay, those are all examples of monomials, one grouping of numbers and letters that don't have plus signs and minus signs involved with them. We can use exponent rules to simplify monomial expressions. And this was taught to you probably starting in pre-algebra and all the way up through Algebra 1 and even probably use some in geometry. So again, this should feel familiar. Product rule. Okay, product rule, this is when we have common bases, and we're going to call that common base A. Okay, so we're multiplying with common bases, and each of these bases has an exponent. We could say this is a to the m times a to the nth power. Well, what we do with product rule is we keep that common base and we add the exponents together. So we say it's a to the m plus n power. So what would an example of that look like with what like we do? We could say, like, for example, if we had x squared times x to the 7th, well, what is the common base? The common base here is x. So we keep that common base and we're going to add the exponents. 2 plus 7 would make 9. That's what it would equal. So that's our product rule, and we use that a lot. Like when we say x times x, well, that's x squared because we add their exponents. 1 plus 1 is 2, giving us x squared. Okay, next we have power rule. This is when we have a base raised to a power already, and then it's being raised to a power again. So basically, m, that power, is being raised to another power. What we do here is we keep that common base and we multiply the powers. So for an example, if we have x squared being raised to the 7th power, okay, our base here is x. We keep that base and we're doing 2 times 7 to get 14. So that's the only time we can multiply our exponents, when we have one power raised to another power. And then we have our quotient rule. Quotient means dividing. So this is when it kind of looks like a fraction most of the times. If I had a base raised to the power a to the m over a common base, okay, the same base raised to a power n, what we do here is we keep that common base and we subtract top exponent minus bottom exponent. So we say that is a to the m minus n power. So for example, if we had x to the 7th power over x squared, okay, we would do, our base is x, and 7 minus 2 would leave us with x to the 5th power. Moving on, our negative exponent rule. Negative exponents do not give us negative valued answers. Negative exponents is about a location change. If we had our base a raised to a negative m power, that means I want to take the reciprocal of my base and then change that negative exponent to positive. So what's the reciprocal of something that doesn't have a denominator? Well, we could think of this as a over 1. So we reciprocal that and be 1 over a, and now my exponent m would be positive. So for example, if I have x to the negative 2 power, okay, we do not like negative exponents most of the time. For what I've seen, usually you don't like having negative exponents until you're in calculus. So we get rid of that negative exponent by taking the reciprocal of x, which would be 1 over x, and then we to make the exponent positive once we've made the reciprocal of it. Okay, location change, nothing else. And then we have our zero exponent rule. Okay, so here, a lot of times we have in math, we say anything times 0 equals 0. It's a little bit different when it comes to zero exponent. Anything raised to the 0 power is not 0, it is equal to 1. And you really can test this out in your calculator. Doesn't matter how big or how small, anything to the 0 power is 0, except, okay, 0 to the 0 power, that doesn't work. Okay, that's undefined. Don't do that one. All right, so if we had something like even any type of monomial, okay, a grouping of numbers and variables and exponents, it doesn't matter. If we raise those to the 0 power, everything would equal 1. So that's a quick overview of our exponent rules, which we have used a lot in the past, and we will use them a lot in this unit. Okay, we'll continue on with the next slide in here in a minute. All right, on these next few examples, we are going to apply our exponent rules. Okay, so we have to look at what the problem is having us do, and the regular numbers do the regular thing. That's what you have to remember. Our coefficients, if it's a multiplication problem, our coefficients will be multiplied. If it's a power problem, our coefficients will be raised to the power. They will divide. They will do the normal thing. The exponents do something different. That's why they have their own set of rules called the exponent rules. Now, when there is more than one rule at a time, then we do need to apply order of operations. So we'll talk about that as we move through these examples. On number 1, we have 5x squared times 7x to the 6th power. So again, times. The regular numbers 5 and negative 7 are going to be multiplied. 5 times negative 7 is negative 35. So that's an example of the regular number doing the regular thing. Then I have x squared basically times x to the 6th. So my base is x. So let's put that down. And our product rule, okay, this is product rule, would tell us that we add our exponent. So x squared times x to the 6th means that we do x2 plus 6, which makes this x to the 8th power. And that's as simplified as it could get. On number 2, we're actually going to have two sets of rules here. Because on this first part, we have negative 2a cubed b in parentheses, and all of that is being squared. And then we're saying times 8ab to the 9th power. So order of exponents is, okay, anything with an outside exponent like this, it needs to be done before multiplication, division, just like any other PEMDAS order of operations problem would. So we have to think, what is the number part? This would be negative 2 squared. The regular number was negative 2, and it has to be raised to the power in the regular way. But then all of our variables with their exponents, we apply power rule. Okay, so this is power rule right here, and that means we multiply our exponents. So a would be 3 times 2, and b, its exponent right now is 1, and we'll multiply that by 2. So let's see what that simplifies to. Negative 2 in parentheses squared is a positive 4. It meant negative 2 times negative 2. A, we did 3 times 2 to get 6. B, 1 times 2 to get 2. And now we need to bring down the parts we haven't used. Times 8ab to the 9th power. Okay, so we're just working this down with order of operations. Okay, now times, now we're going to do product rule. Our regular numbers will get multiplied, but we will now switch gears and we will start adding our exponents. So our regular numbers are 4 times 8 to get 32. For a, we're going to do, our exponents will get added 6, okay, plus 1. And for b, we will have 2 plus 9. And so what does this all simplify to? 32a to the 7th, b to the 11th. So I'm not sure where my number 3 disappeared to, so I'm going to kind of write it in here, and then we'll come back to number 4. Okay, number 3. Number 3 was 54 m to the 6th n to the 4th over 3m squared n minus 10m to the 4th n cubed. All right, again, order of operations. We do not have anything in parentheses being raised to an outside power. So we don't have parentheses. Everything technically has exponents here, but when we're talking about exponents in PEMDAS, we mean like parentheses and then an outside exponent. Again, we don't have that on this problem. Then multiplication or division. Okay, we do have division. Divisions look like fractions. So we are going to divide our regular numbers. 54 divided by 3 would be 18. And then we subtract our exponents for our common basis. For m, we're going to do 6 minus 2 to get 4. For n, 4 minus 1 to get 3. Okay, and then we're going to bring down the next piece, minus 10, m to the 4th, n cubed. Now I'm going to do something. I'm going to highlight up here at the top. It says, when adding or subtracting monomials, combine like terms. Combining like terms does not have the power to change exponents. I'll say that again. Adding and subtracting cannot change our exponents. The only thing it can do is change the coefficient. Okay, but to be like terms, they have to have matching variables and matching coefficients. For example, both of these terms in this problem have m to the 4th n cubed. Because these match, they are like terms, but we will not change that from being m to the 4th n cubed. The only thing that changes is that we're going to do 18 minus 10. We can only combine their coefficients. 18 minus 10 is 8, and that is the solution to this problem. Okay, and that's a very important thing to remember as you are working through these problems. We can only change exponents with multiplying, dividing, raising it to a power, or something like that, not adding and subtracting. So looking at number 4, we have 2k to the 4th times 10k to the negative 7th. So this is going to be product rule. We are multiplying 2 times 10 to get 20. Our common base is k, and what we're doing is we're adding those exponents, 4 plus negative 7. Well, that will give us 20k. 4 plus negative 7 is 4 minus 7, which is negative 3. Okay, so right here, I'm going to highlight this again. We cannot have anything raised to a negative exponent. So just what I highlighted, that k is the only thing touching the negative exponent of negative 3. That's the only thing we have to move. So what do we do? I would consider this a fraction of being over 1, right? Dividing anything by 1 doesn't change its value. Whatever the negative exponent is touching, that grouping has to go underneath the fraction bar. So what we get here is 20 stays in the top. It didn't have a negative exponent over k to the now positive 3 power. Again, it wanted to be k to the positive 3 power, but it can only be k to the positive 3 in the denominator. And that's how we like it written better. All right, number 5. We're dealing with fractions, and that's okay because our calculators don't hate fractions, even if you do. Just use your calculator a little bit more. We have 2/3 r squared s to the 7th in parentheses, all being squared, and then times 1/6 r cubed s. So order of operations will tell us that we have to do anything with an outside power or exponent first, which would be this grouping right here. So that's the piece we have to do first, and that's going to be power rule. Okay, so our regular number, 2/3, we are going to raise this to the second power, or we're going to square it. And then our variables inside, we are going to multiply their exponent. So for r, 2 times 2, for s, 7 times 2. And before I bring down the 1/6 r cubed s, I'm going to keep simplifying this part. So 2/3 all being squared, okay, is going to be 4/9. And then we have r to the 4th, s to the 14th. Now we can bring down this times 1/6 r cubed s. And I don't really need the parentheses because there's nothing acting on them. I don't have an outside exponent or a different number other than this other red part that I've simplified down. So we can show it like this. And now there's just that times dot between. So we're going to apply product rule. So we're going to do 4/9 times 1/6, which is equal to 2/27. And then what are we doing with our variables exponents? We're adding them. So we're going to do 4 plus 3 to get 7. For s, 14 plus how many? Well, there's an implied 1 there. We can see that there's one s. So that's why it doesn't have to write the exponent of 1 because you can see that it's there. So 14 plus 1 is 15. Okay, this is done. There's nothing left to do. We got it down to one monomial answer, one term, one grouping. All right, number 6, it looks a little bit different. Okay, but let's look what we have. We have 14w to the 12th power over 7w cubed, and parentheses around all of this being raised to the negative 1 power. When anything's being raised to the negative 1 power, we are basically going to, reciprocal, I hope that's the right way to say it, everything. We're just flip-flopping everything inside because the parentheses are around the whole grouping. So what we get, we're just flip-flopping everything here. Because if everything was to the negative 1 power, it just means to swap everything from numerator to denominator. So we have 7w cubed over 14w to the 12th. Okay, and then now we're going to do our quotient rule. So we're going to simplify our two numbers here. 7 over 14 is equal to 1/2. And the way that I really like to do my quotient rule here is I don't like to deal with negative exponents unless I have to. So let's just kind of write down what we have. W cubed over W 12th. Now we cancel on a one-to-one basis. So I look at, does my numerator or my denominator have more variables? And I would say that W to the 12th is obviously bigger than W cubed. So I'm going to subtract now, and I'm going to know that my 3 in the top are going to all go away. They would cancel with 3 from the bottom, leaving me with how many in the bottom? Well, I could do that. 12 minus 3 is 9, but they'd be left in the denominator because that's where we had more of it to begin with. So that's another way of doing it. All right, on number 8, we have c over c squared, all being raised to the 4th power, times negative 3c, all being raised to the 4th power. So what we have here, we really have power rule that we have to do twice. Okay, we have these outside powers of 4 before that we can do the step of multiplying these two monomials together. So power rule, that's what we circled here in yellow, means that we have to do this 4. It needs to go inside to the c, and it has to be multiplied to the denominator's c squared. So for the numerator, we have c to the 1 times 4 over c2 times 4. And that would make us have c4 over c8. And we're going to say times. Okay, I'm just kind of keep working it down. We have negative 3 in parentheses. If it's a negative number, I leave it in parentheses until we finish raising it to the power, because it could change whether it's positive or negative. And then for c, we're doing 1 times 4. So again, that regular number, negative 3, is actually being raised to the 4th power. And negative 3 inside parentheses raised to the 4th power will be positive 81. And then we have c to the 4th. All right. Okay, we're going to keep simplifying this. Now we have product rule, okay, timesing. We have 1 times 8. Okay, now we have product rule. I might have messed up this video a little bit, but we're going to do product rule. Okay, we're going to multiply across. Okay, we have 1 times 81 for 81. And then this is all in the numerator, right? 81c to the 4th. So we're going to do c4 plus, or times c to the 4th, which means we do 4 plus 4 to get 8 in the numerator. And c to the 8th times 1 is still c to the 8th. Okay, anytime, it doesn't matter really what it is, we have something like this. Anything divided by its own self, which is what this is, it cancels out to 1. So all of this just equals 81. Okay, on this next part of the notes for this lesson, we're moving on to polynomials. Now, polynomials is the sum or difference of many monomials. What we're doing is we're just putting together a bunch of monomials, a bunch of one terms. We're putting them together with plus signs and minus signs, sum and difference here, plus signs, minus signs. Okay, polynomials can be short, they can be really long, and there's all different types. The highest exponent of any polynomial is called the degree. Okay, so you have to see what is the highest exponent, and that's what names the whole polynomial. So if the highest exponent is 5, it'd be a 5th degree polynomial. The highest exponent is 3, it would be a cubic polynomial. And we'll talk more about that as we go on. Now, standard form. Okay, we always write polynomials with their exponents in descending order. Okay, so let's write that down. Always write descending. Now, what does descending mean? Is that lowest to highest or highest to lowest? Okay, descending means highest exponent to lowest exponent. And that would mean the constant. All right, so what we're doing on these next few examples, 10 through 12, is we are writing the polynomial that's given. It's all mixed up right now, and we need to put it into standard form. So we have to look at negative k to the fifth minus 1 plus 8k minus 3k cubed plus 1/4 k squared. We have to put this in the right order, which is called standard form. The highest exponent is 5, so our leading term here is negative k to the fifth. It doesn't matter what the coefficients are. We're looking at all of these little exponents right here, okay? That's what tells us what order to put the polynomial in. So after 5, the next highest would be 4, but I do not have anything to the 4th power, so we would go to the next highest after that, which would be cubed. So that would be minus 3k cubed next. And then after cubed, we would have squared, so plus 1/4 k squared. And then 1k would just be my plus 8k. And then you should always end with a constant. Okay, that's the only place for it. That minus 1, that's the constant. It's a degree of 0. Again, we'll talk more about that in a minute, but a constant would always be the ending term if it's there. Okay, so number 11. Oh, I guess 12's not on here. Maybe I need to add it. On number 11, we have 18a squared b squared plus 7ab minus b squared plus 4a cubed. When you have two different variables, okay, we have a and b, it is alphabetical. Okay, so highest exponent according to alphabetical order. So maybe I'll write that in there. Okay, highest exponent according to alphabetical order. Now, in alphabetical order, A's come before B's, so we have to go in order of A's highest to lowest exponents before we do something with that just has a B. So that means 4a cubed. Okay, there's no B's in it, and it was fine if it had a B too, but because a cubed is A is first alphabetically and 3 is the highest exponent, it's going to go first. Then we are looking for what has an a squared. Okay, my a squared is right here. So that term, 18a squared b squared, would go next. Seems fair. Now here's where we get some confusion. We have 7ab minus b squared that are left. And a lot of people want to say that this minus b squared should go next, but it does not. Okay, because it doesn't have an a, and this 7ab still has one. Okay, all of my a's have to be given their turn before something with just a b, because b comes last alphabetically. So really it is plus 7ab and then minus b squared. Again, because he doesn't have any a's, and all of these other ones do. We had to go through their alphabetical order process. Now, what would number 12 look like? Let's add it in here. On number 12, we have 5xy squared minus x squared plus 9x cubed y minus y to the 4th plus 2. And again, you might be wondering why I didn't write this in here before, but it won't record right if I try to write examples in before I start recording. Very strange. Okay, I have x's and y's. X's come first alphabetically, so I'm looking for my highest x exponent, which would be x cubed. So 9x cubed y, that whole term, is my leading coefficient, or my leading term, and it has the highest x exponent. Then I'm looking for my next highest x. Okay, I'm not looking at my y exponents right now. X has come before y, so we're looking at them. So that'd be minus x squared. And again, it doesn't have anything to do with the biggest coefficient. It has to do with the exponents. And then my next highest x would be plus 5xy squared. Now notice my x exponents, I'm going to highlight them here, are going 3, 2, and then that would be like 1. So I run out of x's. There'd be no x's left. Now I can focus on something that just has a y to go next. And that's why we can do minus y to the 4th. There's no x's here, even though that y to the 4th is higher than pretty much everything in here. It is not first alphabetically, which is the right way to write this in standard form. So it had to wait till all the x's were done. And then 2 is my constant, it goes at the end. So this would be correct for standard form. Okay, in this last section, for this part of the lesson, we are going to classify our polynomials. Now, polynomials, it says, are classified by degree. Okay, classified by degree, which is the highest exponent in the grouping, and by the number of terms. So use the charts to the left to classify. We're going to fill out these charts. Now, just like every one of you has a first name and a last name, so do polynomials. Their first name comes from the degree, the highest exponent. Their last name comes from how many terms. Okay, so number of terms, that's how many, that gives last name. So degree, let's start. We're going to go lowest to highest here, and I'm going to scoot over just a little bit more. If the degree is 0, okay, anything raised to the 0 power turns into 1, which is just a number. And what do we call things that are just a number? We call them constants. All right, so degree of 0 means we have just a number. That's called, first name would be a constant. If our degree is 1, okay, we have just a regular x and no exponent or anything like that, that's linear. Okay, and that should make sense. We've dealt with linear equations, those diagonal lines, and our x's never had any exponents. Okay, so first name would be linear. If our degree is 2, we just spent all last unit dealing with things where x was squared, a degree of 2, and that was called a quadratic. Okay, so that's its first name if your degree is 2. If our degree is 3, if the highest exponent is 3, we would call that cubic for the first name. If our highest exponent is 4, we would call this quartic. That's how I pronounce it. Not really sure if I'm right. And if our degree is 5, quintic. Okay, that is if our highest exponent is 5. And now I'm on recording, not being really sure on how to pronounce it. I would say quintic, like quintuplets. Oh, makes sense to me. Now the last name comes from how many terms are in the polynomial. So if we have a grouping of just one terms, again, that is called a monomial. And our last name, it's always an omial family. Okay, and it has a different prefix. If there's 2 terms, well, the prefix for 2 is bi, so it's a binomial. 3 terms would be trinomial. And anything that has 4 or more terms, we quit giving it a specific name and we just call it all a polynomial. And real generically, we do call everything a polynomial. It's used, again, as a generic reference. But when we are asked to classify, we're being asked to be very specific. So it is important to use the right terminology. So on number 13, let's go ahead and classify here. The first name comes from the highest exponent in the problem. So we have this 3x, its exponent is 1. There's no other variables in here. So degree of 1 means its first name is linear. Now, how many terms gives a last name, right? So there are 2 terms. 2 terms gives us a binomial. So this guy's name is linear binomial. Okay, that's how he classifies. The next problem here, let's look. We have 9x to the 5th minus x to the 4th plus 2x. So to classify this, again, I'm looking at the highest exponent in the problem. The highest exponent is 5. So we're looking here. That is quintic for the first name. And then how many terms gives the last name? We have 1, 2, 3. Plus and minus signs separate terms in case you're not sure. So 3 terms makes the last name trinomial. Pretty easy, right? Okay, looking at number 15, we just have 24. Okay, notice on this problem right here, 24, there is no x, there is no exponent. Okay, we have it's the exponent that's attached to the variable. So that would be just a number. Just the number 24 is a constant for the first name. And then how many terms do we have? Just one. So number of terms 1 means this is a constant monomial. All right, moving on. We have number 16. I'm looking for my eraser. Excuse me. We have 1/2 x cubed minus 2x squared plus 4x plus 15. Again, first name, highest exponent. The highest exponent is 3. So it matches up here, degree 3. First name is cubic. How many terms do we have? We have 1, 2, 3, 4. 4 or more terms makes this a polynomial. Okay, number 17. Number 17, we have negative x squared minus 18x plus 31. Okay, this should look really familiar to you. My highest degree here is 2. Okay, anytime our x is squared and that's the highest, that's called a quadratic. We've done lots of things with quadratics this semester. And there's 1, 2, 3, making it a trinomial. We've especially done lots with quadratic trinomials, but maybe you didn't really know that. I was calling it by its official names when I called it a quadratic trinomial, but now you do. And number 18, we have negative 3/2 x to the 4th. Okay, so again, highest exponent here is 4. Degree 4 makes this quartic. How many terms is this? This is just one grouping. Okay, we're not adding or subtracting anything else, so that makes it a monomial. Okay, you are going to have a couple different assignments to go with this lesson video where you have to practice your exponent rules and where you have to classify polynomials, but you can do it, not too tough. Do not let yourselves get behind, especially if you are having to do distance learning at this time. Stay on top of your work, you can do it.